The test was great, right? Okay, alright, so slow down. Zero here. So today we're going to talk more about determinants. We're going to continue with chapter, I think it's chapter 4.
Hey, Professor, question.
Yeah?
For the last question, the next one's last question, it was A and B components, right? It was A, no, not B, it was A. Like, so the value of A in it, right?
Ask me after class. Okay, so we're going to continue with determinants. So last time we defined determinants and we defined Laplace expansion. It was sort of algorithmic, it was sort of annoying, so today we're going to learn ways how to work them.
Did you really do Laplace?
We did.
Not in depth.
That was all there was to Laplace, there was nothing else. Right? So, but it's, as you can see, the process is lengthy. You know, if you have like a 4x4, you have to break down to 3x3's determinants, then you break down to 2x2's, etc. So the question is, can we actually make this process easier somehow? And the answer is yes. And so we're going to talk about that today. But before that, does everyone remember Green's theorem?
Yeah. You told us we believe the calculus. You told us we would go on calculus.
Because I heard that in one of your other classes. I don't know, some of you might know that some of you are put on the spot to talk about.
I know it was. I'm not going to
Mr. Green's theorem, I heard, was someone's nickname.
It wasn't me, but I was there. I was there. And it was unfair, by the way.
It was unfair?
It was unfair.
No, it's not.
Wait, what happened?
We were in AutoCAD class,
Yes.
and apparently, I mean, I don't know who he is, but I'm honestly
Oh, it was Amir. That's right. Can you tell me?
the teacher
So Amir, can you tell me what
placed him
Green's
on-
theorem says?
It's the partial derivative of qx.
What?
He said a double one.
Q with respect to x.
Oh, simple.
Right?
Minus B.
Yo, the final's not here yet. That's the whole formula.
I'm saying, yesterday you had to do it in front of like everyone. I thought you'd like at least go home to make sure. You know. I don't know. I mean, your AutoCAD professor might ask you to put it on the board again. I don't know. It's not like a conspiracy or anything, but I'm just saying. You know? No matter where you are, you know, I can come to your room at 3 a.m. in the morning, poke and say, "What's Green's theorem?" You should be able to tell me, right? Yeah, never know when you'll be tested. Is the point. Okay, so you should always know your theorems. Amir can attest to that. Anyway, we're going to continue. We did some determinants by Laplace expansion, and we did, we gave the shortcut for triangular matrices, how to find determinants, just multiply the diagonal elements.
I was reading this matrix book about like matrix analysis book, and actually have triangles, like actual shaped triangles from the book for matrix. Like they actually draw a triangle.
I'm not sure.
Is that to represent like the triangular matrix, or?
I'm not sure. I'd have to read it. I don't think using a triangle to represent a matrix is a standard thing. It's not.
Weird. Okay, that's weird though.
Yeah. So right now we're going to talk about something called pivotal condensation.
Sounds like rain.
Okay, so basically we're going to use this guy, and what he's going to do, he's going to help us to do Laplacian expansion a lot easier. Right, so remember, our trick with Laplacian expansion was choose the row or column that had the most zeros in it, right? But what if there are no zeros, right? Then you'd have to do everything, and it might take a long time. Pivotal condensation can actually help us to get zeros in our matrix and find the determinant for an easier matrix that's equal to the determinant of the original matrix.
Can't you just drag one row by another row to get the zeros?
You could, but there's a special way that you have to do it. Like I said, we're not going to talk about the theorems yet, but row operations do change the determinant. The only row operation that doesn't change the determinant is the type 3 operation, right? Which is what we're going to use in pivotal condensation. itself. This is a way to cut down on right? So zeros are good, right? So we like expanding along rows with a lot of zeros. Well, if there are no zeros, what we can do is do a bunch of row operations to get zeros. Of course, you have to be careful how we do this. It doesn't always, it's not always the same, right? So first thing here is you, steps. Pick an element. Of course, it's a non-zero element. In any row or column. Preferably one where there are already the most zeros possible. Right, but maybe you might not have enough, but you want more. So you pick any random number in any one of those rows where we already have as many zeros as possible. That's 1, 2. Use type 3 operations to fill all or some of
Type 3 was the subtraction?
yeah,
Okay, so my complete guess was correct.
other non-zero. It's not subtraction, it's changing a row by that row plus a multiple of another. Fill some or all, or some of the other non-zero elements in the pivots. Right, so step 2 is sort of like a recommendation. Technically you can use any other row operation, but doing row operations can change the value of the determinant, and I'm going to tell you precisely how. Type 3 operations, it's just aside, type 3 operations violate exactly as defined. So if you take a matrix and you do a type 3 operation on it, then the determinant of that new matrix is going to be the same as the determinant of the previous matrix, right? This is true for a type 3 operation. The other operations, they change. I'm going to tell you how later, but I would recommend that you just avoid it. Avoid the confusion altogether, right? If you do a type 1, which means you switch 2 rows, you have to actually negate the determinant. And if you do a type 2 operation where you multiply a row by a scalar, you have to multiply a determinant by that scalar. I'm going to write that down later, but for now, just know that.
Wouldn't you have to divide your determinant by the scalar?
What?
Wouldn't it make more sense to divide your determinant by the scalar? Like, multiply by the scalar on
No.
one side?
If you do Laplacian expansion, you'd see why.
Oh, I see.
Right, you'd have a row where there's a scalar multiplying it, so you go on the outside of all your things, and you factor it out. So, right? But I'm going to define all that precisely later on, but just know that type 3 doesn't help anything. Type 3 doesn't change anything. Okay, so let's try one. Another note here, which I don't know if I want to make it. Right? Here we can also do column operations. Same way you'd add 2 rows or subtract 2 rows, you can do with columns. Right? But it only works here, not in general. Because it happens to work here because the determinant of the transpose of a matrix is the same as the determinant of the matrix itself. But in general, column operations are illegal. Right? But here it's fine. So what we can do is we can do type 3 operations and kill some guys to get more zeros. Right? So let's do an example. Do I want to start over here?
What are the eigenvalues?
That's the last chapter.
So like next week?
It's the last chapter. We're going to do the last chapter. Okay. Just going to do this one. So you'll notice that this is a 3 by 3 matrix, and it has no zeros. Okay? So what we're going to do is we're going to want to put zeros in there.
And
So let's see how we're going to do that. So now the determinant of this guy is actually going to be equal to the determinant of, let's do a type 3 operation, right? First of all, we're going to choose who our pivot's going to be. It can be anybody we want. I can pick this guy, right? This is a 1, it's a nice, right? It's easy to use a 1 to kill everything else, right? Now you have to do a type 3 operation. Right? Now type 3 operation says you replace a row by itself plus a constant times another row. Meaning the row you want to replace, don't multiply it by anything. You have to multiply some other guy by something. Right? That's why I said it's very important to do it exactly as defined. If you multiply another guy by something, you actually change the value of the determinant. Right? Type 3 operation exactly as defined won't. So here I want to replace the second row with a row that has a 0. So what I'm going to do is I'm going to take this row and add it to a multiple of some other row. My first row is going to be a nice one. Right? So let's do that. What can I do? I can take row 2 minus 2 times row 1. Right? So I'm replacing row 2 by itself plus a constant times another row. And then I would get what? 0,
3, and 7.
what?
-7.
Okay. Now if I replace row 3 by row 3 plus 3 times row 1, what do I get?
No, it's -3, right? Oh, it's, no, I'm sorry. It's -5. I'm sorry. You just took the test.
Okay. This one?
9 plus 4 is 13.
13.
Wouldn't it be quicker to use the bond bars to determinant?
You can do it if you want. Okay, so this is actually equivalent to the determinant of that. What's the determinant of this? Now I can just expand along the first column. Right? It's going to be a lot easier. I only have one 2 by 2 determinant to worry about. So this is going to be equal to, remember, plus starts at the top left. And so this is going to be plus 1 times 3 minus 7 minus 5, 13. All right? 3 times 13 is 39 minus 5 times 7. So remember, alternatively, if you had just originally just expanded along this row, what would the determinant look like? It would be, you'd have plus, minus, plus, right? And then you'd have 1 times minus 1, 1, 4, minus 2 times minus 2, 3, 1, 4, minus 3 times minus 2, 3, minus 1, minus 1, right? So I end up having to do 3 2 by 2 determinants. But if I do a type 2, type 3 operations to kill zeros here and now expand along the first column, I have to do 1 2 by 2 determinant. So I really just get rid of a lot of computations that I would have to do usually. And the determinant will stay the same because I did a type 3 operation.
So ideally, we'll always use periodic condensation for the determinants.
Yeah, it's a very efficient way to do it. In fact, if you tell a computer to find a determinant, odds are it will do this first and then find a determinant. It's just a more efficient way to do it, less computations.
Or do the triangles too.
Right, if you wanted to go further and then kill a zero here, you could.
Yeah.
Okay? So that's a way to get to a determinant quicker using Laplacian expansion. Laplacian expansion is nice when you have a lot of zeros. If you have none, make some. You make them using a type 3 operation. Right? You can make them using others, but it changes the value of the determinant, so I would encourage advise against doing that.
That's it, really?
Let's do this another way then. B. Now sometimes they've actually asked this in a final before, I think, by reducing A to a triangular matrix. Right, so we learned that if you had a triangular matrix, all you have to do to find the determinant is just multiply along the diagonal, and that gives you the determinant. So let's do that with this guy. Let's say we actually wanted to go further. I didn't want to compute any smaller determinants, and I just wanted to multiply numbers. I could actually do that. I can actually probably just start from this step. So what would I need to make this a triangular matrix?
You need to stick with the 5.
I need to get rid of the 5, yes. How do I do it?
Add it by 2 times row 2. No, sorry, it's false.
Can you have to do the exact way of type 3 again?
Come again?
And add row 3 to row 2 and divide by Can you do like?
Try to do it without dividing by
Can you
anything.
can you
thing
do
is,
like
multiply row
5
2 by
times row
2 and
2?
then to row 3 and then do it again.
Times 5 row 2.
Row 3 minus
5 row 2 minus 3
row
row
3
3.
plus 2 times row 2 to get into 1, and then you can delete the middle row with that 1.
Plus row 3,
You could add row 2 and row
and
3.
then we could work with row 1 so we can make sure.
Yeah, that's
Wait, do you have to?
Well, if you work with row 1 to get a
Yeah.
0, you get a 1 here.
no 2 times row 2 plus row 3 to get a 1, and which you can use to take away your second row.
Come again? 2 times row 3.
Yes,
So you want to change
to
this.
6, and then add that to row 3 to get 1, which can be row 2 with.
3 times row 3.
No, just do 5 row 2 plus 3 row 3.
Why is there a
Okay, so you want to change this guy, you said?
No, row 2 times 2 makes 6. Now add that to row 3 to get 1.
Row 2 times 2 is a type 2 operation.
Where are we
I want to avoid, I want to use type 3 operations.
Exactly.
No, but you
Type
know,
3, yes.
I'm keep my so R3 plus 2 R2. 2 is a constant, so,
So R3
plus 2 R2.
plus 2R2, that's a type 3 operation, right?
Yes.
You can do other types, but I want to avoid them for now because I have to explain how they affect things. Okay, so next time we'll talk more about that. Okay, so this is a type 3 operation, and what would that result in? 0. Add 2 to this, I get 1, and
Now we can use this to take away the second
okay, so now what?
row. R2 minus 3 R3.
Negative 3 or 3 plus R2?
You said
R2 minus 3 R3.
that's not a type 3 operation.
Oh, dang it, you're right. We can't change row.
Jhevon,
This is hard.
what if you, from that first one you have in that board, if you do
Oh,
row 2 plus row 3, and
negative
then that
7
new row you add to row
R3 plus R2. Right?
Negative 7R3. I want to kill this guy, that's the goal.
Because you flip the
You can't flip it. You can't flip it.
Use fractions.
Can you add a row?
Yeah, you can use fractions. Fractions are valid.
Can we just like R3 minus 1/3 R2? Can we keep pushing?
Okay, that would give you 0. That would give you 0. Now, if you do, this guy would be what?
Wait, that's negative 7 over 3 minus plus negative 7 over 3. So that's negative 10 over 3.
This is minus 1 plus 7 over 3, right?
Negative 7 over 3.
No,
Oh,
it's negative
subtractive.
negative is positive 4. 4 over 3.
Come again?
4 over 3.
Oh, so you would have,
4 over
right. Now you multiply these guys.
3 times 4 over 3 is 4.
1 times 3 times 4 over 3, which is this guy. You get 4.
That's
It's just
enough.
arithmetic.
Everyone wants to avoid fractions, that's why.
Yeah, but you avoid it to the last step. I mean, here we're pretty much at the last step.
Yeah.
Right. So next time we can actually expand this to type 3 operations. I'm going to talk about properties of the determinant and how they can change based on row operations. But type 3 operations don't change it. So as long as you do this guy, you don't have to.
So it's over?
Yeah, we're done.
Is it 4 done? Is it 4 done?